The temperature, this critical temperature can be measured. I can give you a heat capacity of this device, I can give you a heat transfer with air, and if you measure, for example, the time it takes for it to warm up, you can take a formula and compute what is the critical temperature. So what happens here is the following.
Now it's a superconductor.
What you said is the Meissner effect for type 2 superconductor. And now it kind of locks and levitates.
But at the starting, you have to apply some forces, or it automatically
I
starts?
need to apply some force. I need to apply some force to place it there and take it out. So let me show you a little bit different experiment.
No, this rotation is because he applied the
No, he just placed it and also moving. And that's why I'm worried.
He's giving. I mean, you cannot place it without any force, right? His hand is shaky.
So here.
Yeah, I mean,
And interestingly enough, it also works like this. And it's not rotating by itself, of course. I need to rotate.
You need energy, right?
no, that's why I'm worried. I mean, he placed it and it started.
No.
Oh, it did. I just pushed.
You just pushed, right?
And the path is defined by these two magnets.
Yeah, that I understand.
Yeah, so this is what can happen. And there is another small demonstration. Oh no. It was close. So the point is that it doesn't want to have magnetic field inside, because magnetic field, the change of magnetic field, it makes eddy currents. You know, this kind of what microwave does to warm up the field. So what happens is that the surface, around the surface, there are currents, induced currents, and it expels the magnetic field inside.
It's like a diamagnet, right? It's like a diamagnet.
It's perfect diamagnet.
Pure diamagnet.
That will drop down when you spin downwards.
So this is what I told you is about type 1 superconductor. It doesn't want to have any magnetic field inside. There is another type of superconductors when you place impurities inside. So where you have impurities, the magnetic field is actually allowed, but in those small regions, just in small regions. And when I push it in the magnetic field, this kind of holes, so to say, they are filled with a magnetic flux, and adding or removing magnetic flux costs energy. So essentially, it costs energy to move it, to push it inside and to take it out. So this is why I am applying some force, and this is why I can do it like this. I can place it beneath. I am pushing it inside. I'm doing some work, and now the amount of energy it requires to go down, it's like the gravity pulls it down. So gravity is not strong enough to give it to counteract this force. So it takes work to take and out, to move it closer and move it away. Both take both.
It's rotating because you tilted?
Yeah. It's because I tilt. I can push it a little bit. I see. Yeah. So it wants me to do some work. Like this.
And basically, this there is a magnetic field opposite to your magnet.
Yeah, exactly.
Produced
Opposite.
inside the superconductor.
Yes, exactly. On the surface. And what else I can do? I can pin it. So here I can rotate it and it's rotationally symmetric. But over here it is not, and I can pin it like this. Okay, it's too warm. I need to cool it down a little bit more. Maybe here. Yeah.
Okay, the temperature is 93.
Okay, here we go.
What is this? Is
You
this
can
a
see
puzzle?
explanation. No, it's not a puzzle. It's a cone slices. So this is a stellar orbit, you know.
Okay.
So another one experiment I hope I can show you is this. I can lock it at some position.
I think it's equivalent to placing a satellite in gravitational force like
This one?
stationary.
Yeah, it's in a sense.
I mean, this balancing, this is same as the placing satellite in stationary orbit. There you balance the gravitational force, right? Here you balance the magnetic
You balance it with your velocity, with your orbital velocity. This is a different one.
Okay. Now it's stationary. You wanted to see it stationary?
No. I mean, but okay. But when you tilt it,
No strings, you see? No strings.
So
it stays there until it's cold.
Yeah, until it warms up.
Right.
So until you're correct. Yeah. Like this. I can move it from this magnet to this magnet, and here it can rotate. And I hope it's still cold enough. It's not cold enough, but yeah, it's already too hot. Do you guys want to hear what's going on here? And maybe questions? Yeah, great.
So here it's rotating because of the field is different.
So because of the symmetry, so this is kind of, you see there is no symmetry, so
Yeah,
when
yeah.
you place it down, it's kind of locked. Here it can rotate. This one is however you rotate, it's the same, right? So when you place a superconductor here or whatever device, it doesn't care the orientation because it's all the same. So when you spin it, it just continues spinning.
Okay.
So this is what it was. So here is the story. Do you guys know what is superconductor? I think you do. Yeah.
No, I don't. Do you?
So the story is the following. This device has inside a superconductor. Superconductor is material such that it can conduct electric current without any resistance. So you solved it? Not exactly, but good enough. Huh? So if you wait 10 minutes, I will let you know. If you wait 2 minutes, just yeah, excellent. Okay, maybe we will discuss later. So here is so what superconductor is. It's something that's superconducting, meaning that if it has current inside, there is no resistance for it. It just flows around. Now, there are interesting magnetic properties of this device. Here we have a magnet. All are magnets, and these are pretty strong magnets. So you can see the metallic ruler is kind of very strongly attached. And I can use also this to show you how strong this magnet is, but it can break. so these are very strong magnets. And if I place the superconductor here, it doesn't care, doesn't know about it. But something different happens when I cool it down. When it is below some temperature, some magic happens with the superconductor, and it becomes what we will see in a second. So I got liquid nitrogen too. I pour it here. I wait until it cools down. I think it's good enough. Yes, so we have a superconductor. Now it is below this number which we call a critical temperature. Below this number it is a superconductor. Above it is like this, like some normal metal or whatever. Yeah, some normal metal. So now when it is superconductor, it doesn't want to have magnetic field inside. So yeah, just let me show it. It starts to expel it. Like as soon as I push it close to magnetic field, it doesn't want to have it inside. So you can actually feel how hard it is now. You can take and push it. Just don't touch the superconductor. You don't want? Do you want?
Sure.
Just push it down.
So it's going down because.
Yeah, you push it, but still it doesn't want to have magnetic field inside.
Sure.
It's a little bit too warm already, but below the critical temperature, it is super hard to push it to push a magnetic field inside. So, for example, trains can operate like this. If you have a superconductor, you can have like a strong magnet, and trains can flow without any resistance.
Right.
There is a problem to solve here, if you want, guys. So the question I usually ask is the following. So there is some temperature below which this guy is superconductor. My question is, how can we measure this temperature here? Can we do it? And if you can just ask me any question. I will try to answer you. Like
So the problem is to measure the temperature
at which it's not superconductor anymore.
Okay. Yeah, where it comes down below the
Right now, liquid nitrogen is minus 77 Kelvin. So it's 77 Kelvin. And when I place it over there, I assume that it is cooled down to this temperature. So when I take it out, it's 77 Kelvin.
Right.
Now the surrounding air starts to heating it up. So air around us is around like 295 Kelvin. At some point, it's not superconducting anymore. So at some number between 77 and 295, it is not the superconductor.
Right.
My question, what is this number? And how can we measure it?
So the time it takes, the temperature outside, with the time it takes to not
Time is a
have,
good number. It's not actually, so it is related to time. You will need to measure a time,
Yeah.
but as soon as you know the time, how much time it needs to warm up, you can measure. You can say what is the temperature if you
Right.
do some math.
Right, right,
Yeah, but the time is actually it's what you need to measure.
right,
Yeah.
right.
Yeah.
So the time would be when it starts to
Yeah.
drop.
Yeah.
Right.
When it drops on a plate and not.
Right.
Yeah.
So we measure the time from when we start